Hello, we are still back to the OCV series discussion. Everyone should already appreciate the handy PVT sensors, including the RCC, which may help us tolerate the OCV reasonably from the design phase to the mission mode operation phase. By knowing the more on-die information, we can meet the target PPA together rather than the SOC precisely, increasing manufacturing yield and reliability or safety monitor. But wait a second, someone already raised a chicken and egg image. Could you please think about the caviar image for 5 seconds? Yes, from the on-die PVT sensors, we still apply the on-die elements like the resistor, capacitor, transistor. Intuitively, the block level, DEC, LDC, amplifiers, current source should also have the OCV because of the OCV of the elements. Make sense? Then, how do we make sure the on-die PVT information is precise? Instead, the long on-die PVT information may crop, calibration, or even degrade or break the circuit performance, not to mention validating the SOC precisely. Probably, the long PVT information could even reduce the yield and have safety issues. If that's the case, then we just push this OCV problem to the on-chip sensor or measurement for the high-speed SerDes? I believe the answer is yes. But why did we do that? And how do we improve the accuracy of the PVT sensors? Or equivalently, how to reduce the OCV of the on-die elements? Think about the trimming images for 5 seconds. Correct. For a simple amplifier, the gain from the GM times R can be corrected by trimming the current or the resistance. But by knowing the error information to trim it, we still need to get accurate measurement or sensing, which is another chicken and egg problem. Also, the precision of the trimming is also determined by the resolution of the resistor or current element. To achieve the accuracy down to 0.1% accuracy, we may need at least 1,000 elements. Both the complexity and area will be enormous for sure. Third, we may need to have an on-chip memory element to store this information. Fourth, we may only trim it once and cannot tolerate any environmental voltage temperature drift for the OCV drifting. Can we make another amplifier with the active transistor only to reduce the OCV gain? Sure, we could do that. And the most popular operational transconductance amplifier OTA may have a very high gain. Unfortunately, even though all the elements are active transistors now, the OCV gain is even worse than the mix of transistor and resistor. As you can see, the OCV gain could have greater than 20 dB gain variation, which would have much distortion to sense or measure any on-chip PVT. What can we do? Think about the feedback image for 5 seconds. Good. The negative feedback from the Microelectronics 101 you learned may help you to reduce the open loop amplifier's gain variation or distortion if the feedback element is precise and the open loop gain is big enough. As you can see, the closed loop gain AC is nearly 1 over beta. assuming the AV equals infinity. So we must choose the passive elements like resistors or capacitors as the feedback components to have a good linearity. Then we already know the absolute value of the resistor variation could be plus minus 20%. But if we make a reasonably physical size and layout with a good matching and possibly adding dummy cells, we should be able to have a relatively 0.1% good precision in the resistor ratio. Presumably, a resistor divider of a ratio 0.1 may provide the closed-loop gain of 10 over 20 dB, and the gain error is almost 0.1%. In most sensing applications, that might be good enough. If your PVT sensor or other application requires a higher precision than 10-bit resolution, what can we do? Think about the average image for 5 seconds. Bingo! The average image I learned from Professor Makinwa is very intuitive to me for the DEM concept, and I like to share with you. Even though the original dynamic element matching was proposed by pressure, since we need to resistive divider in the feedback loop, let's focus on the simplest LOCV image in a resistive divider with 2 resistors matching for a moment. For divide by 2 voltage divider, we hope the output voltage is 1/2 of the input voltage, and that holds if R1 equals R2 equals 0.5 times R. On the other hand, if the R1 is 20% smaller and the R2 is 20% greater than the 0.5 R, and the output is 0.4 and the input intuitively, if the R1 is 20% smaller and the R2 is 20% greater than the 0.5 R, and the output is 0.6 of the input. So the average image tells you if we get the output to be 0.4 of the input during half of the time, and to be 0.6 of the input during another half of the time, then we should get the output to be 1/2 of the input voltage exactly after averaging. Since the output is 1/2 of the input voltage after dynamic swapping and averaging, the R1 matched to the R2 equals 0.5 R technically. Then let's dive into the implementation of the DEM. Like the chopping amplifier we've discussed, we need to swap the element dynamically. So first, adding the switches with a small enough parasitic resistance and capacitance is a must. Second, the average is performed through a low-pass filter, which further removes the switch voltage ripple. Third, we mentioned the average was done by assuming 1/2 time is one connection and another half time in another connection. What's the design inside? Bingo! The switching duty cycle must be 50% to meet our half-time assumption. Besides that, what implies more for the average or low-pass filtering? Yes, the implication is clear from the frequency image. Every time you need a low-pass filter may imply the loss of the signal bandwidth. For example, we modulate the voltage up by converting it to the harmonics of DEM frequency and then filtering it out. So our signal bandwidth must be much smaller than the switching frequency. For example, Fin is less than FDM divided by 2. Therefore, the DEM is not practical to implement at a very high speed over wide bandwidth SerDes front end, but we can make it in a very low bandwidth or slow PVT sensor, but high precision requirement. Does that make sense? If yes, we can even extend the DEM to other applications or usage. Again, even though the DEM image is shown in the resistive divider, we can even apply it to any capacitive divider. Therefore, a few high precision filtering can benefit from the high precision resistive capacitive elements. Also, we've known the current source may have a very big OCV because of the headroom, but we can apply the DEM for those nearly DC or very low frequency current source to improve the current accuracy, which may lead to a more precise reference voltage generation for ADC or other precision blocks. For example, Professor McKinwa's very high precision temperature sensor in several ISCC papers does benefit from this DEM a lot, and you can check a few of its state-of-the-art publications. Here are a few summarized images of why we need the dynamic element matching DEM to provide a high precision on-chip PVT sensor over ADC, DAC, current source, and central building block from those fundamental big OCV on-chip elements. First, we started with a chicken and egg image of the PVT sensor, which still used a few big OCV elements to read out the on-chip OCV information to reduce the SoC's OCV issue. Unfortunately, if we don't resolve the fundamental OCV issues of those basic building blocks, resistors, capacitor, current source, or voltage reference, we won't be able to come up with a precise system block like the ADC, DAC, or the PVT sensor to resolve the SoC's OCV issue. Then, after showing the trimming might not be practical to totally remove the OCV, we've shown the feedback can greatly reduce the error from the OCV to push the problem to local mismatch. Part of the OCV, if we want to improve the gain accuracy from 10 bits resolution to 20 bits resolution, then we must apply the DEM, which is also described in a intuitive average image. Like the chopping, the DEM must add a low-pass filter to remove the switching ripple, and the signal bandwidth would be very limited. Most of the very high-precision assistant blocks are designed to support the high-speed SerDes or other wide bandwidth amplifier. Therefore, this DEM is very practical and handy for any environmental drift in a big SoC. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback. I appreciate your comments down below. Lastly, please share the video link with the people who may be benefiting from it.